sent you another email.
When? Just very recently?
Yesterday. Said 9:30 maybe?
God, I missed it.
That's weird. Jay said he could be there.
Yeah, I saw Jay's. Oh, you. Oh, wow.
Maybe I only replied to Jay. I could have messed that up.
Oh, okay. But I saw. Okay, I saw. That might explain it. So what was the time?
9:30. I mean, I could do.
That's
whatever.
okay. That's okay. I'm definitely going to the talk tomorrow. But, you know, an hour should be fine, right?
Yeah.
Yeah, there's only 2 buttons with you.
Oh, we gotta start. I think it's time.
There's about a 2 seconds when you. Troubleshooting step.
When is go? Okay. Okay, problem set 6. And I sent out a message. So finally there's a quiz break, okay? What that means is, you know, there's a quiz due today, right? But there will not be one due next week, okay? So the first problem is 4.1 in chapter 7. There's a baffled piston. Piston has radius A. It's driven at some unspecified angular frequency omega. Find the smallest angle for which the pressure is 0 in the far field. So here's this piston here in this very large baffle. It's going up and down. It's got some radius A. In the far field, we know that there can be nodal cones, right? And make sure you see the geometry here. So this could be a nodal cone, right? The pressure amplitude is equal to 0 on this cone, but it's only it's going to get distorted as you get near the surface, the drive here. Incidentally, you know it has to get distorted because what can occur along here? What do we know about what's going along in the axis here? There can be zeros, right? So they'll connect up with these zeros. Probably look something like this. Okay, but in the far field there are cones, and make sure you understand, because this is the axis of symmetry, if the pressure is 0 on this, at this point, it'll be 0 on that whole cone up there. The condition, the quantitative condition, is that Ka times this dimensionless number, which really dictates the radiation pattern for different sources, right? So this is important. This is the sine of the angle here. This will be this angle right here that yields a null, and we get a sequence of these depending upon zeros of the Bessel function. Right, remember that the field here is dictated by Bessel functions, so we have to find zeros of the Bessel function. You can look those up. They're in back of KFCS, or in an appendix in KFCS. So this is not a numerical problem, but we can formally solve for the angle here. Bring K over here. The first node involves J11, okay, which is, to 3 figures, it's 3.83. So I put that in here. So this is all we can take it, because we don't know the numerical values here. This is as much as we can take it here. If we had numerically specified quantities here, you can plug in and find an angle here. Maybe, right? You're not, remember here, and the information is in the math, you're not guaranteed that this exists. If the sine of an angle has to be less than 1, if this is greater than 1, this quantity right here, a real angle does not exist, right? So, but it'll tell, the math will tell you. You punched in numbers here. It only exists for sufficiently small wavelength or high frequency. Do you get these pressure, you get a pressure node there. Okay, so B is now addressing the axis. Find the greatest finite distance on the axis for which the pressure is zero. Well, we solved for that, and this is the expression that you get for the extremums, right? Both the maxes and the mins. And you remember, you can see it in the math here. For m is equal to 0, you're going to get infinity. That's the point at infinity is an extremum because the pressure goes to 0 at infinity. The next one, m equals 1, as you're coming in from infinity, will give you the first maximum as you come in from infinity. And what this problem is discussed is, what they're interested in this problem is the greatest finite zero. That's going to be R2. That's going to be m is equal to 2. So this formula for R2 gives us this. You can do a little bit of simplification here and get this expression. Okay? And the wavelength here is, of course, the frequency times the wavelength is the speed of sound. So in terms of the parameters of our system here, the wavelength is 2 pi c over omega. And you want to note here that you're not necessarily guaranteed the existence of this, right? It's only if the wavelength is sufficiently small. If you've got a big wavelength, you're not going to get any zeros anywhere. You can't get destructive interference, complete destructive interference, if the wavelength is sufficiently large, right? We've seen this many times. So we get this expression, and again, the existence of this zero is in the math. You have to have this, if this number here, if the first term is not greater than the second term, you're going to get a negative number here, and the radius has to be positive. So that's the math telling you that you don't have any zeros. You only have the point at infinity being a zero. So it turns out in this condition, in this case, the condition here gives us for the existence of R2, lambda has to be equal to or less than the radius of the sphere for this particular case. Now they're going to kind of unite these two, or I don't know what the word is here. The C deals with both A and B here. And the question is, discuss the possibility of obtaining theta 1, that's this angle here for the first minimum. Okay? Discuss the possibility of theta 1 being small. And that's supposed to be R2. I don't know if in your books, it may depend upon the printing, but I made a comment on that in the assignment sheet. It should be R2 over A is much less than 1. And the assignment sheet has a comment on this. So, can we have a small angle and simultaneously a zero close in here? All right? So, what does a small angle mean? What kind of wavelength is going to give us a small angle there? Where you move just a little bit an angle and you go through nulls. I've explained this and we've actually heard demonstrations of it. You need a small wavelength, okay, to have this theta 1 small. But what's a small wavelength going to do to that zero, that first zero? As you come in from infinity, you're going to hit it sooner for a small wavelength. So here's the math. There's different ways you can approach this. I think this is the simplest, but I don't know. We want small theta 1. We have to have Ka much greater than 1. We have to have a small wavelength here. We know that. You can see it in the math. But Ka much less than 1 means the wavelength has to be much less than A. And if you look at this formula for R2, with the wavelength is much less than A, where's R2? It's way out there. Okay? In other words, as you come in from infinity, you're going to hit, for small wavelength, you're going to hit all these zeros, a lot of zeros as you come in. Because there's a lot of them and they're pushed out towards infinity, you're going to hit it early for small wavelength. So you can't have those, they're contradictory can't have both. It's impossible to have both. Okay, any questions on that problem? So the next one's 4.3, a circular piston sonar transducer. We're given the radius and the power, and it's in water. And we're given the frequency, and we want to know the beam width. And remember, there's no real fixed convention on beam widths of major lobe. So it needs to be specified. In this case, we're going to look at it's going to be defined by being 10 dB down on either side of the central maximum, or the axis, the acoustic axis. And my book here, my printing has a part B. Yours probably doesn't, but I put it in the assignment, and it's a good problem. So we're going to do that. They took it out because to do part B, you need to know the next section. So, but unfortunately, for problems involving the next section, this is much better than the other ones in the book, okay? So, I don't know. They shot themselves in the foot. Is that appropriate? I don't know. But anyway, we're going to do it. And I stated it in the problem assignment, right? Okay. Now, we're going to use, we're not really it's not specified where this transducer is, but in all likelihood, it's on like the hull of a ship, right? So it's a good approximation to assume a baffled piston here. Okay. So part A. Here's the information that we're given. Oh, usually, we're given numbers here. We can find the Ka number, this dimensionless number that dictates the radiation field. It's usually a good idea just to go ahead and do it before even thinking about trying to solve the problem. So here's K times A. I think we've done this a fair number of times, and we're just going to keep doing it in this course. K is, omega is equal to Ck for the wave equation. So I get this. Omega is 2 pi times the frequency. And now I have this in terms of all the quantities that were given. So I punch it in, and I get about 21, and that's large. That's a large Ka. I think most people would consider that large, unless you're dealing with you want extreme accuracy. We talked a little bit about this yesterday. But if necessary, we can make an approximation here of a small wavelength. It doesn't look like we're going to do that, incidentally. We may do it in part. No. Yeah, we might. Yeah. Okay. So we'll see. So because of the large Ka number, we're going to have a narrow beam. Our major lobe is going to be narrow. So this is just like related to the last problem, where if you go off the acoustic axis, the smaller the wavelength is, the sooner you're going to hit that null. So what does 10 dB down mean? Right? Well, it means 1/10 the intensity. And intensity is what's appropriate here. Let me explain to you why. Here's the directional factor. Now, the directional factor refers to pressure. Right? The pressure is proportional to this in the far field. Okay, it's 2 times this J1 of V. J1's first order Bessel function, where V is given by this quantity. What's tabulated in the back of the book, in an appendix, Appendix A, I guess, are values of precisely this quantity, but they're squared. So it's appropriate for intensity. They squared them because it's appropriate for intensity. So what you can do there as an approximation, and this will be fine for us, I think usually. We don't need to interpolate here. I don't know if we're going to do any, I can't remember if we do any interpolation, but you guys know how to interpolate if you have a table of values, you assume linear interpolation. We can just look up the closest value. We want this to be, to get 1/10 the intensity as you're swinging off some fixed distance from the source. So we're some fixed distance from the source. We're getting the maximum on the axis, and we want to know how far you have to go out here. Let's go, maybe it's better to go this way. How far you have to go out for the intensity to drop to 1/10. We need to find the value of 1/10 here. Because at theta is equal to 0, which is v is equal to 0 or x is equal to 0, you get 1. The directional factor is just 1. It's normalized. So you can look this up, and the closest value is 2.8. X is equal to 2.8, so that's not bad, two significant figures. And this x here is equal to v, and v is equal to, so we have to have Ka sine theta, and here it is, Ka coming in. I told you, it's usually good just to go ahead and compute it. We punch this in, and we get 7.7 degrees. And remember, the beam width, by definition, is the full beam width. So you have to double this angle. You want to get the beam width. This represents the beam width here. Okay, if this angle represents the beam width, corresponds to the beam width here. Where for the major lobe, the central lobe, the intensity is down by a factor of 10. That's 10 dB down. The beam width is considered to be twice this, as I told you yesterday. So you want to double it. And you can see it's fairly narrow, as we suspected. Okay, any questions? That's fairly straightforward. The next one is an interesting problem. Like I said, that's why, and practical. And that's why I put it in here. So, let's see. So the problem is, the first thing I want to do is verify that we're in the far field. The numbers here, we're 10 meters away from the source. Okay? And we want to verify that that's in the far field. So the first thing you think of when you think of the far field is what? Well, the wavelength has to be large compared, the distance, excuse me. The distance has to be large compared to the size of the source. The size of the source here is like the radius, or diameter, doesn't really matter. If we're 10 meters away, 10 meters is a good approximation, much greater than a half a meter, which is the radius of the source. So we meet that condition. But you remember there's another condition for being in the far field that actually holds in general for all sources. And KFCS underplay this. I don't understand that. We went through all this trouble to find the nodes. Remember the nodes along here? And what that told us, what the information that we got from there is your radiation pattern can be complicated here. You can hit these nodes. And we don't want that we want the simplest possible far field. So that gives rise to this other condition that only comes into play when the wavelength is small. And that condition, I wrote it down generally in the notes, but we'll just use this. This is from the formula here that we saw. Oh, here it is. Yeah. So you remember this R1, that's where as you're coming in on the axis, you hit that first maximum. Right? That's R1. Here's the formula for R1. We want to be far away compared to, well, we don't have to be, remember, we don't have to be really far away. We don't have to have, I don't know how I wrote it here, we don't have to have, so Ka is this. If you look at for a special case, you look at the graph in KFCS, you'll see that you only have to be roughly twice this value, R1, to be pretty close in the far field, at least for that particular case. So you don't have to make it a real strong condition. This one is strong. You have to ensure this is stronger. Remember the squiggly line here? So we don't have to be a huge distance of much greater than R1. So what's R1? We need to calculate R1 and see how much greater we are, or if we are in the far field. So we know this. We have this Ka number. From that, we can get the ratio of the radius to the wavelength. That's straightforward. And it's 3.3. So we substitute that into here. And we find that R1 is at 1.6 meters. So we're at 10 meters, right? No problem. No problem. You don't have to be far away from this. Like I said, just look at that graph in KFCS. Oh, it's in the notes. I scanned it and put it in the notes too. So we've checked off here the fact that we are in the far field. Okay, and it's a lot of people tend to forget the second condition here, but it holds in general. And you'll be doing this in the next experiment, which is next week, right? Okay, you'll be checking that. Now we're going to see why people deal with radiation impedance, right? We want to find what's the pressure amplitude at 10 meters. And we're actually going to find it in the sound pressure level in dB. So how do we do that? What do we know here? Well, we know the axial pressure, and it's the same as the small source, even though this is not a small source. Yeah, we've got lobes here. We know that the pressure, the far field pressure on the axis behaves as a small source. So that's why we're getting this pretty simple formula here, falling off as 1 over r. Okay, so fine, if we want to find this, we just punch this in, right? Well, there's a problem. Do you see it? We're not given this information. What are we given here that's going to specify this in our problem? Power, okay? The greater the power, the greater this U naught will be. Clearly there's a relationship, a monotonic relationship there. So how do we find that? Well, this is the answer in 2 words is radiation impedance. This is really the main reason why it's popular. So what do we know here? We know that the power, which is what we're given, depends upon the radiation resistance, only the real part of the radiation impedance. And this is a formula that you cannot forget because it's just like a resistor. 1/2 R times the peak square of the current. Here, what's analogous to the current is the electrical current, is the velocity. So it's very easy to remember this. Okay, what's the radiation resistance? It can be complicated for a piston. Remember a baffled piston? It can be very complicated. Oh, I haven't looked at that problem yet. I will. I'll get to it and I'll send out a message that came up yesterday. Determining that exactly. Do we need to determine it exactly here? What do we have? Do we have a small source? We have sort of the opposite here. We have a pretty high frequency source. So we can use the high frequency limit here. When the K number's large, whoa. Okay, I'm not crazy about this line of reasoning here. This is always true, okay? So this means implication, right? This is always true no matter what the Ka number is. But when the Ka number is large, we know what the radiation resistance is. You don't even have to look it up because we have effectively a plane wave coming off the source. And we know the wave impedance is rho naught C. To get the radiation impedance, which involves the force rather than the pressure, you multiply the pressure times the area. So the radiation resistance for a high frequency source is just rho naught C times the moving area. Very simple. And that's what I need this here. So but this is, just make sure you recognize, this is true in general here. We showed that, we derived it. Okay, so this is where you need the next section. That's why they yanked it out of there, I think. So the area is pi a squared. Okay, so the point of all this is, if we know this, and now we know the radiation resistance, we can find U naught. So we can invert this. We find U naught, and it happens to be about 10 centimeters a second. Yes, 0.092 meters per second. So now we can go back here. We can find the axial pressure at 10 meters. It's just a plug-in at this point because we know this U naught. So I'm using SI units here everywhere. Here's our Ka and we get a pressure. And to find the sound pressure level, remember, this is the peak pressure, so you got to divide by the square root of 2 when you go to the level, because that's an RMS thing. The reference, this reference here is an RMS reference. So that's why the square root of 2 is right there. So we get 114 dB. So you can see why I left this in. It's a good problem. We're typical specification of a source here is the total power. So how do we get the pressure out of that? Well, as you can see, it's actually not very simple. It involves the radiation impedance. Okay, any questions about that? The next one is 5.1. Oh, okay. So this is again a non-numerical problem, right? And there's a lot in this problem, and this is good. These are good. I think these are pretty good problems here. So here's the idea: we have a baffled piston. Okay, so there's an infinite baffle here, rigid baffle. And we're going to take into account here the mechanical, this is a transducer, right? This source is a transducer. Has an electrical side, we say it has an electrical side and a mechanical side. More on that in the transducer course. Mechanically, the standard model here is it's a damped harmonic oscillator. There's some stiffness, there's some dissipation, and some inertia. That's the mass here. So we're just assuming we know these values. You can think of it, we know these values here, the stiffness, the damping, and the mass. It's radiated into a fluid that has some wave impedance or specific acoustic impedance of some rho naught c, it's unspecified. And they say Ka much greater than 2. I'm not really sure why that 2 is there, but I'm not going to worry about it. It's large Ka, okay? So the wavelength is small compared to the size of the source. So we're going to need to deal with radiation impedance here to get anywhere with this problem. So what's the radiation impedance in this limit? Again, this is easy. This is the tiny wavelength here. A plane wave is coming off this thing. And then I didn't draw this very well. A better way to draw it. So we got this piston and this infinite baffle here. And we're in the high frequency limit. A better way to draw it is, it just takes a little bit more time, is we have essentially a plane wave coming off here. And then as you go, yeah, this gets pretty tedious. You can see that it's going to weakly diffract here, right? And this is just this dashed line is just a rough boundary. It falls off. It's not abrupt. It falls off smoothly, right? But the idea here is that when we're in the small wavelength limit here, when we have this, which is Ka much greater than 1, we're going to have a pretty good beam of sound here. We're going to have a pretty good beam. But it will diffract. It will always, they have to diffract in a uniform medium, at least. So, but the point here is, right near the source, we've got, it's a nice plane wave. So we can use we know that the radiation impedance, which involves just right near the piston there, it's going to have a resistance and a reactance. We know what the resistance has to be. We just talked about this. It's going to be essentially that for a plane wave, but because we deal with force here, we have to multiply the pressure times the area. And remember, this is the pressure divided by the velocity for a plane traveling wave. we multiply by the area to get the force, which is that's the useful impedance for a transducer. We want to deal with the force there, not the pressure. And what's the reactance of a plane wave? I see very near here, I see this plane wave. What's the reactance? Nothing, right? It's just like a string. When you drive a string up in a semi-infinite string, there's no interplay, there's no energy transfer back and forth between the fluid and the piston here. There's no reactive part. It's purely resistive. Okay, now why is this important? Well, the first thing they ask us is, what's the resonant frequency? And again, that's useful from a practical point of view, because often, especially sonar systems, often you want to drive on resonance to get the biggest amplitude. We'll talk a lot more about that in the transducer course. So the resonant frequency here of our driver, not worrying about the electrical side, is where this harmonic oscillator resonates, right? But it's not in a vacuum. It's got this fluid. It's loaded by this fluid. So it's going to be, there's going to be greater inertia in general, right? So how much? What is it? Well, we showed quantitatively that the effective mass here, the total inertia, you've got this mass, what you see, what the external agent who's driving this thing sees is, this system sees this, the actual mass of the piston plus this effective inertia due to the fluid, and that's the radiation reactance x divided by omega. But because we're in the high frequency limit, this is small. Right? So this quantity is going to be much less than m. So it's just m. In this case, it's like a vacuum. Okay? The resonant frequency is not being affected by the fluid in this limit, in this case. In general, it's not true. It can be huge, as I pointed out to you yesterday. Okay, so that's the first part. A, what is this, 5.1? What's B? Sketch the frequency dependence of the radiated power if the transducer is driven with a force of constant amplitude. So this is, a response curve or tuning. We have a bunch of names for this. Tuning curve sometimes. It's very typical in acoustics. And you've already seen it in the lab, I guess, with the... Well, you actually just look for modes there, okay, for the first lab. But it's very common to sweep frequencies, to slowly sweep frequencies, look at the response of an acoustic system. And often you're sweeping with, there's some drive amplitude variable is going to be constant. And in this case, we're going to take the force to be constant. So we're going to imagine slowly changing the frequency from a relatively low value to a relatively high value. We're keeping F constant. And we want to see how the radiated power changes. So what's the radiated power? Well, here it is. Remember, this is general. And in our case, just like in the last problem, the radiation resistance here is simple because we're in the high frequency. It's simple in the high frequency and the low frequency limit. If you're not in one of those limits, then you got to deal with whatever, Struve functions, or you have to deal with. It's more complicated, right? But here in the high frequency limit, the radiation resistance is just this, okay? So that's good. What about, here we are again, just like in the previous problem. What's U naught? Is it a constant? Does it depend upon frequency? I don't know, probably not. What's constant? That F, typical case, okay? So how do we get at this? How do we connect this? This is a response. How do we connect that response to the drive? The answer is impedance. So the external agent that's driving this sees the sum of the two impedances, as we discussed. So the total impedance here is the mechanical plus the radiation impedance. And we just need to deal with the modulus, the amplitude here, so we'll square it. It's convenient to deal with the square here. And we know that the impedance is what links the drive and the response. Impedance always has the form of drive divided by response. And in this case, the drive is this force amplitude, and the response is the velocity of the moving surface, peak velocity. So that's how we do it, right? That's why acousticians love impedance. Once you know this, you've got a link between between the drive and the response. So we have to do a little bit of algebra here. What is this quantity in our case? Well, I didn't even write it down, did I? You all know what the impedance of a damped harmonic oscillator is, right? So you from 3119. So you can see it in here. It has a real part that's just given by the mechanical resistance. The imaginary part is this. Okay, and where this vanishes, you get resonance. Remember 3119? So I've added the real parts here and squared them. So this is going to be the total real part squared plus the total imaginary part squared. Here's the real part. We have just the mechanical resistance and the radiation resistance, and we know what the radiation resistance is. Here's the reactive part for the oscillator, the mechanical reactance, and then we have the fluid, the reactance of the fluid, but that's small here, so we neglect that. So the point is, we can solve this for U0 squared. We know this. This is just some specified constant. So we can find U0 in terms of F. And I guess what I did at that point was, looks like I skipped something here. I can then substitute the result for U0. I can substitute the expression into here to get the power. So you can go through those steps. Okay, it looks like I just went to you can go through what's in this implication right here. And here's what you get. This is what we want. We want the power as a function of frequency. We're slowly sweeping frequency. And this is just going to be a constant for us. We want it in terms of F because F's a constant. So what is this? Before we sketch this, there's some questions here. Where's the stiffness-controlled regime? The stiffness-controlled regime is where the stiffness controls what's going on. Only the stiffness is relevant here. It's low frequency. When I have an oscillator, a harmonic oscillator, and I'm driving with a very low frequency force, the motion it's relatively really slow, right? And what's going to dictate the amplitude there is just the spring constant. The inertia is not involved because it's going so slow. So that's the stiffness-controlled regime. You remember this from 3119? And so the frequency is very low, so it's when this term is dominated. However, there's another condition here to be in the stiffness-controlled regime. We want, if the stiffness is the sole thing that's controlling the response, we have to make sure that this is bigger than this. Technically, okay? So that's a second condition here. We want this. This not only has to dominate this, but it has to dominate that to be in the stiffness-controlled regime. So that's a second condition here. The inertia-controlled regime is when I have a very high frequency, I have a small response, the mass is going back and forth at a very low amplitude. The stiffness is just not in play here. If you're driving a harmonic oscillator at a way above resonance, and you got this small amplitude here, it's going back and forth very quickly. If you cut the spring, you're not going to see any difference. Okay, the stiffness is not playing a role there. Basically it's because the amplitude is so small. So that's it's the mass that controls the response. So in that case, that's the opposite limit. This is much greater than S over omega. Okay, and again, we should add this should add the condition that it's beating out these resistive terms here. So that's omega m is much greater than that. Okay, so here's a sketch of, here's how we usually think of this. When people look at this, they usually see this, okay? But if you're not accustomed to that, you can easily go from here to here, qualitatively. For resonance here, because so on resonance here, you know we're going to have the maximum response. So that's when this is equal to 0, right? So you can see from here, this is a positive quantity, this is a positive quantity. Each of these terms here is a factors or terms, I guess, is positive. To maximize this, it's going to, for these being constant, remember f is a constant, we want this to be 0. So that's going to be, we're going to get the maximum power at resonance. You knew that was the case, but I just want to point out, you can see it in the math here. It's when this is equal to 0. So that's going to be our peak. And what's nice about this formula is, this general formula is, we have an expression for the maximum power. That can be useful, right? So you just zero this out, and I put it right here. Here's the maximum power. That's good. Now, what happens as we go to low frequency, let's say? At low frequency, as we go to lower and lower, this is going to dominate. Eventually, we become stiffness controlled. And because this is becoming very large, it's going to go to 0. And how does it go to 0? How does the power go to 0? It goes to 0 as the square of the frequency. Do you see it in here? As this becomes very small, we can forget this in the stiffness controlled regime. We can forget this, and I see the power varying as omega squared. So what do we have here? A parabola, right? Unlike what KFCS have, because back then they had a graphics artist, actually, who didn't know anything about anything. Well, I shouldn't say that. But they're not around anymore. So anyway, this comes in like a parabola right here. What happens at high frequency? The inertia controlled regime. Now this dominates, and now it's going to fall off as 1 over omega squared. So this is, this is falling off, typical 1 over omega squared there. Good problem. Okay, any questions? Okay, I think there's one more. Yeah, okay. So this is 5.3. Find the radiation impedance of a pulsating hemisphere. Okay, now I put into the problem assignment here is you need to baffle this because and there's several reasons. Can anybody think of some reasons here why you need to baffle this? One of them, if you didn't have this baffle and you technically just had a pulsating hemisphere, what's bad about this? What kind of source is this? It's a dipole. It's not a monopole. There's no changing volume. Our theory doesn't work. Okay, it'll radiate, but you'll have to, God, is that in the book somewhere? I actually don't know. But it's going to be somewhere in some book. Okay, it's going to be. There's two problems there. You want to close this off to make it a monopole. So let's suppose you close off the hemisphere here to make it a monopole, so we can use our monopole theory. Now you've got another problem. What's that? This thing radiating. What's the radiation pattern going to look like for this? Well, it's complicated for a piston. It's going to be probably even more complicated for a hemisphere, right? Unless the wavelength is large. If the wavelength is large, it's very easy. And you're all going like this with your head up and down, but you have no idea how many people have asked me about the quiz problem. It's the quiz that's due today, okay? It tests your beliefs, okay, in this. When you have anytime you have a small source, it's going to radiate isotropically. It's very simple. It's equivalent to a pulsating sphere. So, but in this problem, it's not necessarily a small source. So without this baffle, you've got a hard problem. You've got a hard problem to solve. Okay. So why does the baffle help here? Well, because I know that any point We're interested in the sound field out here, right? Any point, if you're at any point, you can't tell the difference, and this is exact. You cannot tell the difference between this problem, the hemisphere in this rigid baffle, or the related image problem where you remove the baffle and you have an image hemisphere that you imagine there going with the other sphere like that. You cannot tell the difference. That's an amazing fact, and there's no approximation in there. And we talked about that in the last chapter, right? The whole idea of an image source. So, now we can, having done that, we can now do the problem. Let's see, part A. Find the radiation impedance of this pulsating hemisphere here. Well, it's the same as this. The sound field here is going to be the same here. But we got to be careful. The radiation impedance is defined to be the force divided by the velocity. Right? In our case, where everything's moving in phase, all the moving elements have the same amplitude and they're in phase. It just ends up being the force of the surface on the fluid divided by the velocity of the surface. The force is the pressure times the area. And what's the area here? Yeah, the area is half the area of a sphere. Our problem right here, we have half. We're just using this to get the sound field out here. Okay, but the radiation impedance here, you got to follow exactly what it says here. You've got to take this to be half the area. This, which relates to the field out here, including on the surface, the reason we know that it's this is because it's going to be the same as a full sphere. So this is our full sphere result. This is I guess is a little confusing here, right? So here we have to be careful to use the area of the hemisphere. Here the sound field is the same. We know the only way we know the sound field here is we know it's the same as the sphere. We wouldn't want to try to calculate this. Okay, you wouldn't want to waste your time. You know it has to be the same as this by the image relationship here. So we know the wave impedance here. It's just given by this. We've seen this many times for a spherical wave, where this angle theta here, the phase at the distance A, r equals A, on this hemisphere, is given by this triangle. You can get it from the right triangle. And there's the area of a hemisphere. So the radiation impedance here will be just half the value of a full sphere because of that. This is the same as a full sphere. But because of that, it's going to be half of a full sphere. That's the radiation impedance. And this is true for any frequency. Small source, high wave, large wavelength, and anywhere in between. This is exact. So the next thing here is to look at is B, which is find the radiation resistance for high frequencies. Okay, this is good that this isn't a problem. We've gone through this in lecture a number of times. Let's do it again. When Ka, you look at the right triangle diagram. When Ka is large, what's theta A going to be? It's going to be small. All right? So this reduces. You just set theta A equal to 0. You can just go ahead, it's easy here. Cosine of 0 is 1. So we get this. And you can see that it's purely resistive, right? Does that make sense? Should the impedance here, should the radiation impedance be purely resistive here? Yeah, we're in the high frequency limit. So if you look at it locally here, you see a plane wave coming off there, purely resistive. Okay, and I guess they asked for the power. Again, this is the general formula. We know the radiation resistance. It's identical to the radiation impedance because it has no imaginary part. So we just plug it in and we get this expression. And you can go back and check for what we did with the sphere. This is half the power of a sphere, which it has to be, right? The total power coming out here is going to be half the power of a sphere that's radiating in all directions. So that's a check on our solution. Finally, part C. Now we're going to look at the other limit, the low frequency, the small source, low frequency limit. Now there you have to be a little bit more careful when you let Ka go to 0, you say, well, theta A is equal to 90 degrees. Well, you can get away with that for the phase. Remember, our impedance has a phase in it. E to the I pi over 2, that's I, otherwise known as I. You can't, if you set theta A equal to, for the cosine of theta A, if you set theta equal to pi over 2, what do you get?
0.
You get 0. And that is a first approximation because Ka is small, but you've gone too far. So the nice thing about the triangle here is you can get the approximation for Ka. It's really simple for the cosine of theta A. The cosine is going to be this over that. And when theta A goes to 90, this approaches 1. So the cosine is just going to be Ka. And we went over this in class, but I'm just pointing it out again. So you put all this together, and now you find that instead of the impedance, the radiation impedance being purely real, it's now purely imaginary. It's purely reactive. And this is due to these surfaces stretching and compressing. The energy that's being delivered there, almost all of it, just comes right, it shuttles back and forth between the source and the near field. Again, it's like driving a pure capacitor or a pure inductor. And there's a little bit of, there's a little bit of phase there. There's a little bit of resistance, and that's what the sound that gets out, that little bit. It's not an efficient radiator. And how do we quantify this? How do we think of this? Radiation mass. You take the radiation reactance divided by the frequency, and that's the effective loading due to the fluid. And we're asked to calculate it here. It's straightforward. And the way this is usually stated is it's compared to, the mass loading is compared to the amount of fluid, the mass of the fluid in your source right here. We talked about that in lecture. So that's the natural way that's easy to remember, and it's physical. So it's the mass due to the displaced fluid due to your source here. The mass of that is the hemisphere volume times the density. If we put that underneath here, we find 3. And that's exactly the same ratio we found for a sphere. Okay? So, and it has to be the radiation mass is 3 times, for a sphere, it's 3 times the mass of the fluid in the sphere of your transducer. For the hemisphere, we have half of the radiation mass, but we also have half of the displaced mass is half. So they cancel out, and we end up with the same factor of 3. That's what's happening there. Okay, any questions? Okay.